Okay, I had this train of thought and I wanted to turn it into a video. Uh, it's a weaving path, so get ready. I was watching some video and up came a related video that was Richard Dawkins quoting Richard Feynman saying that anyone who claims to understand quantum physics doesn't understand quantum physics. Now that's an interesting statement about quantum physics, but what struck me was the epistemology behind it. The thing is, how could you know if you don't understand something? How can you tell somebody else that they don't understand it? So I thought of an example. If somebody says that the sun is boiling cheese, I don't understand how the sun actually works, but I know enough to know that it's not a vat of boiling cheese. This could be confirmed. I could do experiments that would show that it's not consistent with what it would be like if it were a giant vat of boiling cheese. So Feynman's point on quantum mechanics is really that we don't have any theory of quantum mechanics, any model of how it works that is any better than that. That's any better than saying the sun is boiling cheese. Now, on the other hand, when we're talking about this kind of stuff, we're munging together a bunch of different theories. The whole idea of quantum mechanics has actually several layers. On the one hand, the quantum mechanics that Bohr or Feynman really had faith in was this idea that, okay, over here we have a model, a mathematical model, we know how to operate. And over here we have measurements that we know how to take of our perceptions. We know how to use measuring sticks and measuring devices of all kind. And this model, when we operate, it's able to predict what kind of measurements we'll get. When we set certain things up ahead of time, we can reproduce these. If we can't set things up ahead of time, but we can do the measurements to figure out how they were set up, we could derive the results. And so that part of the theory is very well demonstrated. And it awaits somebody to prove some phenomena that it can't make a prediction about. Really, the only problem with it is that it's so difficult to calculate. A lot of times you don't want to use the theory. You don't want to use quantum mechanics to figure out how to send a spaceship to the moon. That would be ridiculously unnecessary. But in terms of its accuracy, nobody has really anything, nobody has anything at all against it. And that's one set of theory. But what Feynman was pointing out is that to really understand the why of this model, we need to understand something more abstract about it, or perhaps less abstract, more tangible. What does that mean? What does it mean to us? Are there really multiple universes or not? And on that kind of level, nobody has a decent theory that they can really... I shouldn't say that, because I do think there's a decent theory. And I believe more in one family type of those theories than others. So I think there's, maybe more than one decent one. But I mean, nobody has one that they could get on their pedestal and claim to understand it. Because we need these levels to really understand quantum mechanics. You don't want to just say, well, I have a mathematical model and for some reason it can predict that. You want to know more. You want to know what's going on even more inside there. There's maybe many different ways we can imagine this model applying. The universe's collapse, or many histories, and we're just a cross-section. Or rather, we just see a cross-section. We're a part of the whole as well. All right. So then, also in that thread, there's the science student. He was talking about that science means mathematics, and that empiricism without math leads to superstitions, which I found funny because I think as good as math is, the deification of mathematics, or pretending that finally in mathematics we know or speak the language of the universe, another quote by Feynman, is sort of, that's superstitious. I mean, why do we believe in math? It's for practical reasons. Math is about patterns, and there's patterns occur in nature. That doesn't mean patterns, are math itself, The math is happening in our mind. The patterns are happening in nature. Okay, patterns that can be modeled mathematically. It's not a done deal if all patterns can be modeled mathematically, or what that really means. I mean, there's different kinds of math. You know, there's math traditionally is this formulaic written math, but there's a tradition of geometry, and you can define something like a conic section, you know, geometrically, the point, the line, you know, space. We can define those. In terms of you know, these idealized perfections that don't have any of that written formula. Uh, so if we want to say that math is any way of describing patterns, then even then we can't say that the math is in reality. We just say that the math matches up. It models the reality in that sense, and you know, and that's what I think. You know, and we believe in math corresponding to nature because there's been so many times when we just played with math for fun, and then later on, centuries later, we find out, wow, this math we played with for fun all this time is really practical. You know, for thousands of years, philosophers formalized logic just because they thought it was interesting and useful to do so. Hundreds and hundreds of years later, we come up with computers. It's like, thanks for all the, you know, work. I mean, we had all of this stuff of how computers would have to think. In other words, this formal, simple logic, and then we had computers apply it to. Or the conic section. You know, they thought the conic section was the conic form and the conic sections were really interesting. You know, 300 years BC and further, and yet. Then, surprisingly, you know, centuries later, when a theory of gravitation came along, conic sections describe the possible shapes of paths in gravitational fields. That's sort of an interesting coincidence, you know. And quantum mechanics, in a way, is another example of applying this idea that there's this sort of patterns can be discovered. Sometimes we have a mathematical idea and the pattern isn't quite right. And for example, one of those is the point. Okay, the mathematical idea of a point, the geometric idea of a point, doesn't work as well as other ideas. Okay. Now, it seems like hoping that math is reality, to me there's a silliness there. That'll never happen to me. And here's why. It's like we're creating this thing in our mind, mathematics. We have accrued mathematics, you know, and it forms up more complicated and complicated. But it's modeling reality, okay? And then, you know, but at certain points it didn't. Like, you know, Zeno's paradox is about breaking things down using a mathematics that doesn't work to describe reality. You have to use a different mathematics. You have to use calculus to describe what happens when you break crossing the path into an infinite number of parts. Calculus. You know, his simple math didn't work. So we're creating a better model, and it's as if people want reality to be math. It's like, well, they want eventually the model like to turn into reality. Like, if you make your model really, really accurate, suddenly, wing, the magic fairy turns it into reality. See, so I have no ever expectation of why a model would ever become reality. No, even if it was possible to have certain knowledge, even if it was possible to you know, apprehend the world and take it inside, just that copying process makes it a separate thing, and then they'd start to diverge and be separate things. I mean, just in principle. But luckily, I don't think I'm faced with that because we can't get perfect copies, and so it's really, you know, mathematics is beautiful. Paintings are beautiful. Flowers are beautiful. You know, lots of things are beautiful. But if you get so in love with it that you have some sort of crazy idea that the impossible is going to happen, then, you know, you should just rethink that. So now,